Name of the paper: Comparison of 3 modulation technique for single phase half bridge 5 level inverter based on level shifted BWM. Authors: Noureldden Farkash, Abdelhadi Ramdan, Sami Mohamed Tamasas Elrais. Electrical and Electronic Engineering Department, University of Benghazi, Libya. Content of the paper: Introduction, Diode clamped multi-level inverter, Modulation technique, Simulation design, Experimental design, Simulation and experimental result, Comparison of simulation and experimental result, Discussion of the result, and conclusion. Introduction. The word inverter in the context of power electronics is power conversion circuit that operate from a DC voltage or current source and convert it into AC voltage or current. A multi-level inverter not only achieve a high power rating but also enable the use of renewable energy source. Some of application of multi-level in renewable energy sources such as photovoltaic, wind and fuel cells can be easily interfaced to a multi-level inverter system for high power application. The multi-level inverter has smaller voltage steps than that of the conventional inverter, which lead to the production of higher power quality waveform, reduce the dV on dt stresses on the load, and the electromagnetic compatibility concerns. The main type of multi-level inverter: series H bridge, diode clamped, flying capacitor. Design diode clamped multi-level inverter. When designing a diode clamped multi-level inverter, we must choose the number of switches and the clamping diode. The number of switches is n-1 product 2, where n is the number of the level. Number of clamping diode is n-1 product n-2. The bus voltage VDC is distributed across the capacitors C1, C2 to Cn-1 as shown in the figure. Modulation technique. By the modulation technique, we mean that how to generate the necessary train of pulses to control the inverter's switches according to the required output voltage, reference voltage. The modulation algorithm used to drive the multi-level inverter must be aimed to give the voltage level required for each leg. The transition in the proper switches configuration is done by other algorithm which can be hardware or software implemented. There are several ways to classify modulation technique, and switching frequency can be divided multi-level modulation into 3 classes: fundamental, mixed, and high switching frequency. High switching frequency modulation are the adoption of standard BWM to the multi-level, and they supposed to switch a very high frequency about 10 to 20 kHz. Pulse width modulation technique. There is phase shifted pulse width modulation BSBWM and subclass called level shifted pulse width modulation, phase disposition BD, phase opposition disposition BOD, and alternative phase opposition disposition ABOD. Pulse width modulation technique. There are 2 important factors must be known. First, the amplitude modulation ratio MA, which is the ratio of the peak to the peak amplitude of the reference AR to the peak amplitude of the carrier AC. MA equal AR divided on the number of the level minus 1 product on AC. Second, the frequency modulation ratio MF, which is the ratio of frequency of the carrier FC to the frequency of the reference FR. MF equal FC divided on FR. Sinusoidal reference in phase disposition technique SIBD. In this figure illustrated sinusoidal reference in phase disposition technique SIBD. The carriers in this technique are in phase and they have the same frequency and amplitude, but they are different in this DC offset to occupy contiguous bands. It's based on a comparison of a sinusoidal reference waveform with vertically shifted carrier waveform as shown in the figure. Sinusoidal reference phase opposition disposition SBOD. This figure illustrated sinusoidal reference phase opposition disposition SBOD. The carriers in this technique have the same frequency and amplitude, but they are different in the DC offset, and the two carriers above the zero axis are in phase shifted 180 degrees from those below zero axis. Also, the reference in this technique is sinusoidal signal as shown. Sinusoidal reference alternative phase opposition disposition SABOD. This figure illustrated sinusoidal reference alternative phase opposition disposition SABOD technique. In this technique, each carrier of the method is shifted by 180 degrees from its adjacent one as shown. Simulation design. The simulation part has been done via MATLAB Simulink to simulate the modulation technique and the power circuit. The simulation design is constructed of three main parts as shown in the right figure: the control circuit, modulation technique block, the power circuit, inverter power circuit block, and the AC load and measurement block as shown. Experimental design. The experimental design is constructed of five main parts: control circuit, inversion circuit, isolation, power circuit, measuring block. The four train of pulses have been obtained via computer programming, where four triangle carrier of the same peak-to-peak amplitude carrier amplitude equal 1 volt peak to peak and the same frequency but different in DC offset of 1.5, 0.5, minus 0.5, minus 1.5 have been generated to cover all the range of the sinusoidal reference variation of amplitude of the reference is equal 4 volt peak to peak, which centered in the middle of the triangular set. The four train of pulses that is exported throughout the parallel port will be inverted using 7404 logic NOT gate to operate the lower switches T1, T2, T3, T4. The 8 train of pulses that have been obtained from the parallel port and the inversion circuit will be isolated in the isolation circuit using 4N to 5 OBT coupler to isolate the power circuit from the computer to prevent any damage to the computer because of any fault in the power circuit, and to prevent short circuit occurrence between the inverter switches. The power circuit that has been used is the single phase half bridge 5 level diode clamped inverter. It constructed from 4 DC supplies, each of VDC equal 20 volt. 8 switches have been used in the circuit, and the switches is the IRF 530N channel power MOSFET. 6 clamping diodes have been used in this circuit, which are BY359/1500. The load that has been used experimentally is reactive load of 100 millihenry inductor and 100 ohm resistor. The practical implementation of the 5-level inverter circuit setup in the lab. In this figure, illustrated the practical implementation of the 5-level inverter circuit setup in the lab. Simulation and experimental result. SIBD technique at MA equal 1 and MF equal 15. The right figure illustrated the current and voltage waveform via simulation oscilloscope, and the left figure illustrated the current and voltage waveform via actual oscilloscope. Simulation and experimental result. Second is BOD technique at MA equal 1 and MF equal 15. The right figure illustrated the current and voltage waveform via simulation oscilloscope, and the left figure illustrated the current and voltage waveform via actual oscilloscope. Simulation and experimental result. Third is ABOD technique at MA equal 1 and MF equal 15. The right figure illustrated current and voltage waveform via simulation oscilloscope. The left figure illustrated the current and voltage waveform via actual oscilloscope. Comparison of simulation and experimental results. Those figures shows the output voltage RMS values versus the amplitude modulation ratio at MF equal 15 via simulation and experimental for the 3 techniques. Comparison of simulation and experimental results. Those figures shows the total harmonic distortion values versus amplitude modulation ratio at MF equal 15 experimentally and via simulation for the 3 techniques. Discussion. From the output voltage RMS value point of view, it's clear from the figures all the 3 techniques have similar behavior, which is increasing linearly with MA at MA less than or equal 1 and increase non-linearly at MA greater than or equal 1. From the total harmonic distortion point of view from figures, the SIBD technique is almost better than the other 2 techniques, SABOD, SBOD, for most of MA, and the SABOD, SBOD are almost the same. Conclusion. The inverter's output voltage quality is one of the important criteria to govern the inverter quality, and the modulation technique affects the output voltage quality because it affects the output voltage harmonic content. The goal of this paper is to compare between 3 modulation techniques, SIBD, SBOD, SABOD, from the total harmonic and output voltage RMS waveform and number of level point of view to know the difference between them. Simulation design has been done via MATLAB Simulink in addition to experimental setup in the lab, and the required result for the comparison are obtained. The 3 techniques via simulation have been compared separately and they are compared experimentally, and the same conclusion has been gotten from simulation and experimental design. Also, comparison between simulation and experimental results have been done, and they are found to be coherent.